Okay, test, test, test. Okay. All right, so continue to the slide. So basic terminology for the computer networks. We talk about the baud rate and bit rate. What's the difference? Nice example of this. On this case, is baud rate is 10 times, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. 10 times means how many times the signal changes. Okay, bit rate is how many bits can be sent per time. In this case, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, which is count to 10. On the other side, I have baud rate 10, but I have bit rate to twice. How come? Because I have previously, I only have the 2 different levels. In this case, I have 4 different levels. 0, 0, 1, 1, 0, 1, 1, 0. Okay, so your receiver needs to be much sharper than before, but if your receiver can do this, then I can double the bit rate, meaning I can send more information. I can send a double information than before. That is a bit rate. So in this case, by making multiple signal levels, 2 times more signal level, I can send a 0, 0, 1, 1, 1, 0, 1, 1, which is count to 20. So baud rate is how many times signal change. Bit rate is how many bits can be sent. Okay. So bit rate is controlled by the baud and number of signal levels. Remember this. So if my receiver is, in this case, it is 2 bit. This is 1 bit. If my receiver is 16 bit, I could have more finer resolution. Okay. So these days, your a Wi-Fi receiver usually comes with a 10 bit. If you're using an expensive device, that may comes with it 16 bits. Above the 16 bit, it is military level. Okay, so physical media. So signal travels through the medium and represent the bits. We understand this. So when I speak over the air, my information is transferred and you can hear it. Okay, wireless network same. So if you change the status, so I just want a quick check. Do you understand what is I and what is Q? I phase and Q phase? So in the signal, if I think we did this before. So some says about that they never heard about I and Q. And I checked the textbook of the high school. So your high school checked it. High school covers this. It really doesn't matter where you studied. In the US, in Korea, I think the most common word is checking. We cover this topic in the physics. Okay, so basic introduction. What is I and Q? In phase and Q phase. When the signal travels, there is always following this pattern. Okay, at the same time, if you look at this detail, I can say, okay, 1 and 0, then your signal travels somehow, you receive it, this phase. Your I phase is shifted, Q phase is shifted. Okay, so if you don't understand what is IQ, it is, you don't need to completely understand, but I thought everybody clear about the I and Q. So whenever you're using wireless media, so your signal travels follow signals in I and Q phase. Okay, you can search the wiki file wiki for the quick references. Okay, let's don't worry about it. So we know that physical media travels the signal travel through the medium and represent the bits. What is 1 and what is 0? Okay, so Nyquist, the genius, the name after the genius, Nyquist bandwidth. Nyquist bandwidth, error-free medium. Given an error-free medium of the bandwidth B, the highest signal symbol rate, baud rate, can be delivered by 2 times of B. What? So Nyquist prove it. given an error-free medium, which is very rare, let's say this error-free medium, like the 5 optics, bandwidth B, the highest signal symbol rate that can be delivered 2 times of your bandwidth. Ah, okay. So bow to the bits, 2 times of the bandwidth multiplied by log 2 m. M is number of signal levels. Okay, we know what the signal level is. Previously 1 and 0. Oh, how about 1, 0, 0, 0, 0, 1, 1, 0, 1, 1, which is 2 to the power 2, 2 to the power 1. Okay, how many bits? How many bits? I have 1 bit, I have 2 bits, 3 bits, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. I will 1, 1, 1. 3 times, which is 8 steps, 8 levels. Okay, so let's say I'm using 2 times multiply log 2, m is 2 to the 2, which is 4b. Okay, so if I'm using this a 2-bit level signal, and I'm using a bandwidth B, and how much can I achieve theoretically in the error-free medium? 4 times of B. B means your given bandwidth, oh, I can achieve 4 times the bandwidth. Oh, what if I have 16 QAM? Meaning 2 to the 4, then I could have 2 to the 4, 8 times of B. Okay, so we can keep calculating this. So Nyquist is a genius. Then he proved that, I think it is the character of 1920 to 1940. And he proved that, okay, this equilibrium, and we're strictly following. Okay, Shannon is also the genius. Shannon's capacity is a theorem. Okay, so we human on Earth can achieve the capacity following this equation. Oh, the Shannon's equation. So he taught us what is the limit, what is upper bound, meaning how much can we achieve. But he never told us how can we reach that. So still, is the Shannon's theory. Let me check. Where was Shannon? Capacity. Henley, the Shannon Hadley, Shannon's law. Shannon Wikipedia. So here's no. Claude Shannon, American singer. No. Signal. Nyquist Shannon theorem. Shannon theorem. So 1915. So here's the character of 1915. How about the Shannon is 1915. And what's Nyquist? Nyquist. Oh, no. Nyquist. The life of Shannon is 1945. How about Nyquist? Nyquist. Life. Okay, so his character, he's born in 1889, and he's published is 1917 to 1934. So about 100 years ago. So we still follow his theorem. So Nyquist and Shannon, they defined the upper bound. So Nyquist told us the bit rate we can achieve in a given bandwidth. Okay, Shannon told us, teach us what's the upper bound in a given network. Okay, and none of us told us how to get there. So it's still 4G, 5G, we never reached there yet. So define the upper bound on the link capacity C in the hertz. So it can be used to evaluate error-free bandwidth for a line. So SN means a signal to noise ratio. So capacity is bandwidth multiplied log to 1 plus signal over noise SNR ratio. Okay, remember these two equations. So what's the difference between baud rate and BPS in the Wikipedia? So in a telecommunication and electronics, baud is the common measure of the symbol rate. We know what it is, right? We checked in the slide 2 or 3. Then one of the components that determine the speed of the communication over the data channel. Okay, BPS is a measure of how many bits can be transferred during one pulse. Okay, so BPS is usually baud rate multiplied by number of bits per baud. Okay, so you can read through it. So this is by definition in the Wikipedia. So let's do a simple practice. So example of the Shannon's theorem. So voice grade phone is 3 kilohertz. So voice grade phone, what we are using previously, and I think that most of the phone is converted to the digital media. So we're connecting LAN cable rather than a phone line. So a long time ago, we're using copper wire to communicate over the air. So that copper wire can cover about 3 kilohertz. The bandwidth is the B, and it is 3 kilohertz, meaning I can hear from 300 to 3.3 kilohertz. Okay, that is what your ear can decode. Okay, typical SNR is 30 dB. 30 dB, we have ability to convert it from a dB to the power, actual power to the dB. Why do we using dB? To calculate in the log scale, which is more straightforward and easy to calculate. So dB is 10 times a log base 10 and SNR. Okay, so meaning the 30 dB means 30 dB is 10 log 10 of S sub n. What is Sn? Then I can divide 3 is log 10 Sn. 10 to the 3 is S over n. S over n is 1000. Okay, simple as this. Then go back to the Shannon's capacity. Okay, C is my B, which is 3K log to 1 plus SNR, which is about 30 kbps. So voice grade phone, if I have voice grade phone, then I can communicate about 30 kbps. Okay, by using the Shannon's theorem. Simple as this. Okay, so higher bandwidth B is higher capacity, and higher SNR is higher capacity. Meaning your signal, your voice, if your voice is clearer than a background, then you can deliver more, like we do. So if I speak in the very silent office, you can hear my voice clearly. Then I can speed up. I can talk fast, and you still understand. But if I talk in a crowded area, like the coffee shop, And if I speak, it's very hard to understand. Then I have to speak slowly, then you maybe understand. Okay, so the higher bandwidth, meaning if you can talk in the higher bandwidth, how can I say a higher bandwidth? So let's say your phone works in the 300 to 3.3K, but your Wi-Fi works in a 2.4 gigahertz and 5.4 gigahertz. So higher frequency, it usually give you a higher capacity. Okay, so we're gonna talk about this over the semester. So let's practice one more time. So the quick quiz, can the signal be weaker than a noise? Now we understand what it is. Oh, signal can be weaker than noise, right? Is it true? So we know what the Shannon's capacity is, theorem. What if the signal is weaker than the noise? What happened? Can we still communicate? Nobody? Let's think about for 1 minute. Then I'm gonna pick the student who wasn't actively participating. Okay. So I'm gonna ask you Jung Ho-jin and Seung Jae Kang, Pan Kelly, Son Ye-eun, and Yu Jung-min. Okay, I hope everybody following the class. Okay, let's think about 1 minute. Okay, ready?
Professor, I
Yeah.
didn't get the question.
You
What does that
don't get the
imply by
question.
noise?
Okay, so we talked about the Shannon's theorem. Okay. Okay, in this case. Okay. So we talked about what is Nyquist bandwidth, and we talked about the Shannon's capacity. In the Shannon's capacity, by definition, your capacity of your network is B times log 2 1 plus Sn. Sn means signal over ratio, a signal to noise ratio, SNR. So your signal is much clearer than noise, then I can hear your voice. What if your signal is lower than a network and lower than a noise?
Can noise be other than Professor? Sorry.
Go ahead.
Question. Can noise be other than the noise that's like noise that
Your
comes
background
from
noise,
like
your environment noise,
can it
which
be like
hinders your communication.
that hinders
Yeah.
communication?
Yeah.
Okay.
What if the noise is stronger than a signal? Can you still communicate? That is the question. Everybody clear about the question?
Yes.
Okay. So Hojin?
Yes.
Yeah. What do you think?
I'm not sure, so I'm guessing, but I think signal cannot be weaker than noise.
Okay, good point. Seungjae?
Yes,
What do you think?
I'm not sure about it too, but I think the signal can be weaker than noise.
Okay. Kelly? Okay. Yeun? No. Jungmin?
Yeah, you can go first.
Yeah, go ahead.
I think signal cannot be weaker than the noise.
Okay. Thank you for your comments. So I try to be more interactive with you guys.
So Jungmin didn't answer yet.
Okay.
Right.
Jungmin, you want to say?
Yeah, but I'm not sure, but I think signal can be weaker than noise.
Okay. All right. Thank you all. So let's talk about this. So your opinion could be different. So any one of you can give me a reasonable background and maybe support this comment. Anyone? No?
Professor?
Yeah.
I think if the signal is distinctive, like goes up and down, I think we can still hear the signal.
Great point. Who's speaking?
Hamin?
Good point. All right. Anyone else?
My name is Seungjae Kang, and I said that we can. The signal can be weaker than noise, because if the lower signal does not make the S over N to be something like very close to 0 or negative value, then I think we can still hear the signal. So that's why I.
Okay, good point. Okay, so let's assume the case, and let's talk about English first. What if the signal is weaker than the noise? Can you still hear that? Oh, let's say you went to the coffee shop, and your background is much louder. But if you are focused on something, so like there is a handsome guy or a pretty lady communicating, so you may listen more carefully, right? Even your background is much noise, but you can hear what they're talking about. Okay, so network is the same thing. So even the signal is weaker than the noise, we still can communicate. Let's talk about it. All right, so assume the capacity is a 50K BPS and the bandwidth is 1 mega, which is so 1 mega bandwidth is very nice, but 50 kilo BPS is very low, but it's still very poor, but let's assume this. The required SNR, so it's B 1M, and 50K BPS is 50K BPS. Okay, then we can compute this. 50K is 1M log 2, 1 over SN. Okay, then it goes to 50 E minus 3 is log 2, 1 plus SN. Then 2 to the 50 E minus 3 E minus 3 is 1 plus SN. So SN is 2 to the 50 minus 1 is C over B minus 1. Okay, so if you compare, so if you calculate this number, minus 1, which is 0.035. If you compare this value to dB, it's minus 14.5. So what this means? So signal is 35 and noise is 1000. Okay, so even your noise is about 30 times bigger, we still can communicate. Okay, that is a wireless network, and this is what the Shannon says, and it is correct. So think of the spread spectrum communication, then we're going to talk about it, and transmit weak signal over the large bandwidth. It is feasible. So the baseline for this is UWB. Ultra wideband is using this background, and it is well established communication method. So spread spectrum communication meaning. So fundamental communication meaning, oh, I have a network frequency. I can usually communicate like this. Very high signal over given noise. Okay. The wide spectrum is in the given frequency, rather than I'm using strong and sharp, but I'm using wider and weak signal. Even there is some spike, I still can communicate because I'm estimating my patterns. Okay. So the candle signal can be weaker than noise, yes. Even 30 times is weaker, then we still can communicate. So relating Nyquist and Shannon's, assume B is 1 mega and SNR is 24 dB. How many signal levels are required to achieve the max rate? Okay, let's calculate this. Oh, since we talked about dB, I have to convert it to a power level. 24 dB is 10 log 10 SM. So 24, this one, if I calculate it back, it should be 10 over 2.4. Then 24, right? It goes to 2.4, right? So SNR should be 10 over 2.4, which is 251. And using Shannon's capacity, I'm using 1 mega 10 over 6 log 2, 1 plus SNR 251. Then calculating this gives you, this is about 256, right? Which is 2 to the power 8. Then 8 times of the M. Therefore, it is 8 Mbps. Okay, using Nyquist theorem to achieve my upper level, 2 times of bandwidth log to M, which is 2 times. So my C is given, my capacity is given. My capacity is 2 times of my bandwidth was 1M. Multiply log 2 M. I want to know what is M. Okay. E to 6 and the 6 is a 4. 4 is log 2 M. What it should be. So if you do 2 to the power 4 is M. So which is 16. Clear? So if I do this again, so I have 1 mega of the bandwidth. SNR is 24 dB, and I want to achieve the max rate. How can I achieve max rate? By step, I can compute the SNR what is required SNR. Then SNR to the power level is a dB to the power level, and using the Shannon's capacity, I checked the theoretical upper bound. Then using the Nyquist, I understand how many levels do we need. Okay, this is how you solve the upper level, and we're still using this in the when the 4G and 5G comes to the market. Okay, SNR levels we support, and how many signal levels what we support. Okay, so let me give you example. say Wi-Fi standard 802.11 and 2.11. Wikipedia 802.11 and speed Wikipedia. Oh, how can I go to English? Okay, and I think I can go to English from here. Setting. No. EN Wikipedia. Wikipedia. Go to Wi-Fi. So when the new network comes to the market, okay, maximum link rate always presented, and frequency we are using, okay. And if you see the detail, Wi-Fi 802.11n, something like this. Okay, so in here, so 64 QAM saying I have 64 level. BPSK binary BPS, meaning I have 1 bit. QPSK quadrature, I have 4. 1024 QAM means I have 1024, 2 to the power 10. 256 QAM is 2 to the power 8 levels. Oh, levels we talk about. Okay, here we talk about levels. And we talk about the channel capacity. I have 20 megahertz channel. And I talk about the data rate, BPS. Okay. Oh, now we have ability to read the text sheet, the spec sheet of the Wi-Fi and the LTE, all these things. Okay. So these are all related to Nyquist and Shannon, and this is how we calculate it. Everybody clear? Okay. Now we have ability to read the spec sheet of it. So let me check the. Let me see here. Participant. So Miss Pang is not in the class and she's not responding. Is she still in the class? No? Nobody knows? Okay. So most of you are junior and senior, right? And I thought you guys very familiar each other. Maybe not. Okay, so come to the point. So encoding. Now we have to map binary 2 bits to the signal. Ah, okay. Encoding. So if I go back to the point, encoding. Okay. So I have to make my digital signal to analog, meaning I have to map my binary bits into the signal. Example, low means 0, high means 1. Something like low, low, high, high, high. Okay, 0, 0, 1, 0, 1, 1, 1, 1. Okay, we call this NRZ, non-return to 0, and problem is long period of silence of the high signals are possible. Let's say my information is 0, 0, 0, 0. If it is repeating 10 times, it is very hard to follow. Why is it hard to follow? Because every receiver comes with the reference signal. What is reference signal? Okay. So let's say I'm sending 1, 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0. Okay. Say I'm a receiver. I'm keep maintaining in the middle value. I'm keep maintaining a middle value by checking what is high and what is 0. There is no capacity. Okay, so middle value. By the capacity, I have 1, I have low signal, high signal, low signal. So based on this threshold, I can make decision what is higher and what is lower than me. Then this is charges. This threshold is coming up when it is 1 value and goes down when it's 0 value. Okay. And in this case, very hard to distinguish what is 1 and what is 0. And in here, I'm sharply increasing, and sharply dropping, sharply increasing, sharply dropping, increasing, increasing, decreasing. Okay, the reference signal, and also the signal has oversampling. I think we talked about oversampling. 1, 2, 3, 4 times, 1, 2, 3, 4 times, 1, 2, 3, 4 times, 1, 2, 3, 4 times. Why do you do this? Because whatever it is changed, it's very hard to detect what has been changed. So you do oversampling and you make a vote. Okay, I think it is 1. I think it's 0. I think it's 1. I think it's 0. In this case, 1, 2, 3. Oh, it has changed. 1. Okay, I think it's 0. I think it's 1. It is very clear when it keep changing. But if it is oversampling and threshold comes in here, was it 0? Okay, how many bits? Is it 0? Is how many bits? Was it 0? How many zeros you talked? Okay, like a human, computers also very fuzzy about this, very prone to error. So when the zeros continue, how many zeros? It's not clear. When it's keep changing it, oh, it is much clearer in the signal level. There's this basic signal processing. Okay, go back to the point. So long period of silence or long period of 1 gives you, oh, was it 1? Was it 0? Was it 0? How many zeros was there? So the sharp detection of the edge is very hard. So we do oversampling, and the reference signal is changing and keep strictly following the patterns of it. Okay, therefore receiver loses track of the reference signal, and we call this baseband wander and clock recovery. Receiver loses clock synchronization. Ah, okay, we're gonna talk about what is clock synchronization. So more schemes, and NRZ is a very basic level. When it's 0, it's 0. When it's 1, and it's 1, it's 1, which is too simple and very prone to error. Then we have a clock. Every system has a clock, and we do synchronize it on the clock. So 1, 0, 1, 0. This clock is just crystal on your computer, on any computing devices. It keeps giving you 1, 0, 1, 0 in high frequency. If I have more frequency, meaning I can sample more in a given network, I can send more information, and it is more clear to decoding. So let's say the simplified crystal only 2 times of your signal, then the Manchester coding gives XOR with the bit stream with the clock, meaning if your signal is close to a clock, meaning when it goes high, it's changing. Oh, you're also changing. It is changing your change. Then it is easy to synchronize it. But if you compare it to up, we're changing. Okay. Oh, I synchronize it in here. Then it is very hard to synchronize it again. Then at this point, I can synchronize it. Oh, synchronization period can be longer. Then it's very hard to synchronize it at the same time. It's very hard to follow the reference. But if your signal pattern changes more frequently, I can synchronize it here. I can synchronize in here. I can synchronize in here, here, and here, and here, and here. You can synchronize more frequently. Then you can confirm your signal more precisely. Okay, then Manchester code. Rather than you sending an NRZ, the sending Manchester code is more efficient. So how do you do Manchester coding? Okay, I have 0 signal, 0, 0, okay, 0, 1. XOR gives you 0, 0 is 0, 0, 1 is 1, 0, 0 is 0, 0, 1 is 1, okay, and it is 1, 1, 0 is 1, 1, 1 is 0, 0, 0 is 0, 0, 1 is 1. You know what the XOR means, right? 0, 0, 0, 1, 1, 0, 1, 1. 0, 1, 1, 0. A, B, A, XOR. Okay, then when the Manchester code is sent, then easy to recover on the receiver side. Okay, the more signal change in a given network. Okay, that is a Manchester code. And there's NRGI is how you decode it properly. So your information is 100101 and you have a clock. And based on that, you make Manchester coding. Then it is transferred over the air. Then this is what I received. This is what I received, the Manchester. Then on the receiver, you also have a clock. Then you do the same thing on the receiver. So 0011, okay, 0, 0011, okay, 0, 01, 0110, okay, something changed, okay, 0011, oh, not changed, okay, 0110, oh, something changed, 0111, oh, something changed, 0110, oh, something changed. Something changed in here, 0011, something not changed. Okay, 0110, oh, something changed. 0011, oh, something not changed. 0011, something not changed. Okay, over this. Then you can say, okay, when there is nothing changed, I said 0, nothing changed. Oh, there is a change, 1, nothing changed. Oh, there is a change. There is a change. There is change. There is change. Nothing changed. Change. Nothing changed. Oh, changed. Nothing changed. Okay. What you intend to send is perfectly decoded on the receiver. Okay. This is how we use the clock in the transmission, and it confirms it's more reliable communication with using XOR. Clear? So we call this Manchester coding. NRG and NRGI is NRG inverted, switch from current state to the 1. So this is how you recover it. Okay. And there is a 4B, 5B encoding scheme. So encode 4-bit simples into 5-bit code. Why is it necessary? So I have 4-bit information, 4-bit simples. The best way to do is 4-bit code. Okay, 0, 1, 2, 3, 4, 15. So I have 4-bit symbols, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1. Oh, this is perfectly matched. Then why do we have one more extra bits, one more extra code on this? Why? Because signal something like 0, 0, 0, 0 is prone to error. I don't want to use this. And something like 1, 1, 1, 1, I don't want to use this. And also 0, 0, 0, 1, 1, 1, 1 and 1, 1, 1, 0, very similar. I don't want to use 1, 0, 1. I don't want to use one of these. So I can make more distinctive pattern if I have one extra bit. Clear? So we call the 4B, 5B encoding. So encode 4-bit simples into 5-bit code. So 2 to the power 4 simple must be mapped 2 to the power 4 code word out of the possible 2 to the 5. Then I eliminate those are very prone to error and make more distinctive patterns. So each code word has no more than 1 starting 0 and no more than 2 trailing 0. So whenever it comes with the 0, I want to eliminate it. So no more than 3 consecutive zeros. Then use NRGI to solve the consecutive ones problem. Oh, we know what the ones problem. Consecutive ones appear, it prompt to error. Therefore, I can eliminate those. Consecutive zeros, they're prone to error. I can eliminate. So it is 80% efficiency. Why? Because I'm only utilize 80% of the 5 bits. I'm only utilize 4-bit code out of 5 bits. Therefore, we call 80% efficiency, and I use 1-bit overhead. Okay, so it is useful, and we are using this pattern. And this is example of the 4B5B encoding. 0000 maps to 11110, and 1111 is mapped to 11101. So in a given environment, each code word has no more than one starting 0 and no more than 2 trailing zeros. 1, 1, 1, 1, 1. There is no 2 ones in the starting, okay? And there's no more than 2 trailing zeros. There is no 3 zeros in the tail. There's no 3 zeros in the tail. Also, no more than 3 consecutive 0. No more than 3 consecutive 0. Eliminate all this. Okay, so this is how we're using. So with the code book, if I receive it, I can recover because my code book is shared between transmitter and the receiver. Okay, so framing. So, okay, I want to finish this slide, so maybe I can speed up a little bit. So framing, so what is framing? The process of grouping bits into frames. So messages or packets. So if I give a long talk, how does this handled in the network? So you make it divided and small packet, then deliver to the receiver, small packet to deliver. This is how the MLB live is streamed over your house. If it's completely recorded, then compress it and deliver to you, then you don't want to watch it. You want to see live video. Then the video is chunk, smaller, then it can deliver, then I can see sequentially. Okay, that is basic framing. So why do we need to frame? So the message is too big. You have to frame it. Okay, so there is many mechanisms on the framing. So byte-oriented framing, which does BySync, binary synchronization communication. Frame is a collection of bytes. Your frame look like this. So centennial characters are used, meaning centennial which is distinctive than others. Okay, so syn is synchronizing, is everywhere. So we want to see what is STX and ETX. This is your body. So you need to decode this body. This is all for the communication. But what you need to do is between STX and ETX. What's the disadvantage of it? So ETX pattern is 1011, let's say something like this. Then in the body, maybe 1011 pattern is there. Maybe. Then it ends the communication quicker. Then CRC gives you error. Then how can you solve this? So, problem with the byte-oriented framing, meaning EXT may occur in the payload and preceded if the DLE, data link escape character, and problem propagates and precede DLE with another DLE. And P2P is something like this payload, it keep losing and your error is accumulated over the communication, which is not good. So how we solve it? We're using count. So before we starting, so we declare how many bits I'm sending. Okay, includes number of bytes in the frame in the field of header. This is example of DDCMP. DDCMP is Digital Data Communication Protocol. We do the very same thing. So header says, this is the, after the header, actual messages are coming in. So I don't have STX. I have STX in the header, but I don't have ATX. Why? Because I have count. I know how much you need to expect. Then the byte-oriented issue is naturally resolved. The count specify number of bytes in the bottle. CRC ensure that the count field is not corrupted. Okay, we're going to talk about CRC in a coming slide. Okay, so this is a very basic communication. So if I review what we discussed today. So today we talk about what is encoding and what is framing. Why is it needed? Okay. So in the communication, the point-to-point So we have to have encoding. We have to have a framing. We have to have error detection and correction. We have to have reliable delivery. We have to have MAC. So let's look into what is an encoding. So if I send it 1 as a 1, 1, 1, 1, 1, 1, 1, then receiver is very confused. How many ones did you send? How many zeros was sent? Oh, I'm going to show you. I'm going to send a distinctive pattern, 1, 0, 1, 1, pose, 0, 0, 1, 1, pose, 1, 1, 0, 0, pose, something like this. Then that pattern is matched to my code book. Oh, that was 1, that is 0, and that is 1. And framing, if I make a long video, if I talk is very long time, then I don't want to make one chunk and deliver to the receiver. I want to make it very small pieces, then deliver. If it is wrong, I can send that portion only. If I make a big framing, if it is one is not delivered properly, then I have to retransmit everything. But if I do framing, I can assure, okay, that frame is wrong, that frame is right. Okay, what if there is an error in the communication? Oh, there was error. How do you know? Checking the counting 1 or counting 0, just make sure at the end, okay, this bit needs to be a 0. This needs to be 1. So we're gonna error detection, error correction is covered in the next slide. Next lectures, and reliable communication. We need to have reliable delivery. If not, I have to send it again. Or maybe you can correct it if it's wrong. Immediate MAG is, if there is more than 1 people, let's say 2 or 3 people want to share this, then how can you make a rule? That is a MAG, okay? So typical communication comes with this. So I have to have encoding source and channel encoder, interleaving, and signal encoding. So we talked about the compressed of the bits and adding redundancy for the code book. Oh, we know what it is now. And scrambles the bits of the consecutive code word to spread the burst error. We're going to talk about in the next slide. And encoding and how can you convert to the analog signal. Then we talked about basic terminology, which is baud rate and bit rate. What is a baud rate? Baud rate is number of the signal changes. Bit rate is many bits, a number of bits you can send per time, per unit time. So more baud rate, the baud rate is signal change, but the bit rate, if I have more signal levels, I can transmit more efficiently. Okay, then we talked about the Nyquist theorem, Nyquist bandwidth, the Shannon's capacity, and how we're using this. And by definition of the Wikipedia, this is baud rate and this is BPS. Baud rate is common symbol rate and unit of the modulation rate and how many times it changes in a signal. And BPS is baud rate multiplied by the signal level. And we did one example with the Shannon's capacity, how we calculate it in a given bandwidth. And SNR is 30 dB. Then from here, I can set, oh, this is the upper level BPS, upper level capacity. So higher bandwidth gives you higher capacity, higher SNR gives you higher capacity. So we also talk about the Shannon's example, Shannon's theorem. So can the signal be weaker than the noise? The answer to this is yes. And assume we check with the, we practice with the 50 kbps and 1 megahertz bandwidth, and SNR would be this using the Shannon's capacity, which is 35 signal level over the 1000 noise level. Okay, so even the signal is 30 times weaker, we still can communicate. So relating to the Nyquist and the Shannon, by practice, assume when your bandwidth given, SNR is given, the levels do we need to have to achieve the max rate. So starting from signal level in a dB to the power level, and Shannon's formula, by applying all this number, so we just tagged it, okay, theoretical limit is 8 Mbps, and by using Nyquist theorem, so how many symbol levels do we need in a given network? Then we check this. When we have a 16 levels, we can achieve 8 Mbps in a given network environment. Okay, we checked it. And encoding,
Can I interrupt?
yep.
I have a question. Like in the Nyquist bandwidth equation that you showed above, like in physical medium slide, like it says R equals 2B times log base 2n bits. That's R means capacity.
Yes, BPS.
Okay. All right. Thank you.
Okay, thank you. So we are here. Nyquist, we talked about this encoding, and we have to map into the signal, map binary to the codebook. Why? Because some zeros, if it is continuous 0, is prone to error. Continuous 1, prone to error. We have to change it. Let's by having a codebook. Okay, codebook says this. Codebook consists of distinctive pattern. Okay, then step by step, we did the information you want to deliver and none return to 0 in the signal level. If we have a clock, every system has a clock. Then we make it to the Manchester coding using XOR. Then if it is this pattern is transferred and received, and based on this, I also have a clock, receive also have a clock, and we have ability to decode this level, and based on this, how you read it, when it is not changed, oh, change, not change, change. Information you intended to transmit is all transferred properly and decoded properly.
Okay,
And we
so
talked about
how do we make sure the clock from the receiver and the sender is synchronized?
Okay, so when let's say you have a Wi-Fi, and Wi-Fi using a same clock and most the computers, right? Also, let's say I sent this information, your clock is synchronized every time it's changed. Every time it change, every time it's changed. Okay. So the question to how can you make sure? So if I show you this pattern, so every packet look like this, sync and sync. Always has multiple of the sync, meaning synchronize on this clock, synchronize on this clock. Transmitter always send the predetermined synchronized pattern. Then based on that synchronized pattern, receiver always synchronized on that given signal. So before the actual communication is established, all the packets comes with the synchronization character. So receiver knows, okay, this is how I synchronize to this packet. Then synchronize on this packet, okay, keep saying. Okay, over the communication, you can synchronize your clock to the receiver.
Does it also apply to the PPP? Like it doesn't have a sync. The point-to-point protocol. Yeah.
The previous one?
Point-to-point protocol does not have a sync tag.
Okay, so P2P as a different mechanism. This is P2P is usually the wired, and before here, there must be.
I see. All right.
After this, there must be CRC. Okay, so every communication should have a sync. Without sync, it is almost impossible to synchronize it. Good point.
Thank you.
Yeah. Okay, go back to the point. 4B to 5B, why do we need to convert it? If the 0 is a consecutive, it is hard to decode it. Therefore, we have some codebook. That codebook is all distinctive, very easier to recover. Then we talked about why do you need to framing and how our communication is advanced. Starting from byte oriented, byte-oriented turns out this EXT pattern is easier to be appear in the body. So we have the counter, which means in the header, which is strict rule, then the receiver knows, receiver estimate, okay, this is the length of payload. It's much easier to communicate. So this is today's lectures. Any question?
I have a question.
Yeah.
If within the framing, if there
Within the frame.
are any errors within like sync or the body, does it skip the frame or does it try to resend it?
Oh, I don't get it. What the question is, if the sync pattern appears in the body?
Oh, I meant like if there are errors within sync patterns or other places like in body, does it resend the frame or does it skip this frame?
Okay, so the two methods. I may recover with the correction, or I can retransmit if the correction is impossible. So before the body, it is all predetermined. Therefore, it is easier to recover. Okay, scene is a scene, start of header, and start of text. Okay, this is all pattern. Okay, that pattern is not that many. The receiver can estimate. Easier to understand. The body is completely random. Then EXT and the CRC. So CRC gives you the clue. Is the message clear? Is the message is not clear? The CRC confirm that, okay, this message is intacted or corrupted. If it is corrupted, how many bits are corrupted? Okay, I can handle this with the correction mechanism. If it is possible, I can correct it. If not, I have to retransmit it. That is basic communication. Does it satisfy your question, or did I not clearly understand your question?
Oh, that was good. Thank you.
Okay, all right. Thank you. Any question? All right, so from next week, we're gonna talk about more detail. And I think today's lecture is like just overview. And I hope you understand what's the Shannon's capacity and Nyquist theorem. I think this is also covered in physics in the your high school, maybe or maybe not. All right. Anything else?
Professor, homework will be uploaded today, right?
No, this Wednesday. I have to cover
Oh,
lecture
okay.
5, then I can give you homework.
Oh, okay, sure.
All right. Thank you. If no, visit my office if you want to. Have a good day. Thank you, guys.
Thank you, Professor.
Thank you.